my research mostly tends to focus on ocean dynamics and ocean turbulence in some way, and in numerical modeling of problems related to that. But what I'm going to talk to you today is about the sort of models that I write in those studies and how they're written. So in particular, I'm very much a user of most of the tools that I'm going to talk about today. So most of the tools are developed, there's groups who are working hard to develop these tools, which I then use. I'll talk about some contributions I've made to this. And depending upon time, I'll talk about the sort of applications I'm using these tools, these tools to study in ocean dynamics. But what I'd perhaps like to take away from this talk is if you have a problem that you'd like to study and you'd like to develop a way of studying it very quickly, and perhaps you don't worry so much about performance, then the sort of tools I'm going to talk about, the code generation tools I'm going to talk about, might be something you'd want to consider. So I'll give an introduction to unstructured finite element modeling. I'm going to give a little background in why this is still, it's at least for large-scale ocean modeling, it's still not that widely used, and I'll give some indications as to why. And then most of the talk, the bulk of the talk, I'm going to talk about how you write codes to study these problems. So I'm going to show the real code and show where the problems are, and why, particularly when you write a finite element model, you can run into difficulties and technical problems and things that are really quite tricky, and how these can be addressed. And then in the remainder of the talk, I'll talk about how you start to address these problems by writing your problem in a slightly different way. And depending upon time, I'll talk about the particular applications that I'm using these tools for towards the end of the talk. So let's talk about the type of models that are used, at least for large-scale ocean modeling. So finite element modeling is somewhat more common in smaller scales, perhaps coastal problems. I tend to work on larger, say, ocean basin scale problems where they're still pretty uncommon. And once you go to large-scale ocean models, structured grids are still pretty much the standard. They're still pretty much the thing that is used. There are other examples, but a lot of the big, widely used codes tend to be structured grid models. So what this means is that we have a nice grid which basically maps the data in your model onto an array in your code. So you have a nice, predictable, sometimes uniformly spaced, sometimes not, grid of data. So if you have a data point here, then it's really easy for the computer to work out what my neighboring data point is there. I mean, that might just be an index increment in one direction in your array. It's really, really easy. They're usually finite difference or finite volume, depending on how you view the discretizations. They're pretty easy to code. Depending on the level of complexity of the model, you can get something going as an individual fairly quickly when you want to write a finite difference code, and I'll talk about why later. And you get a whole bunch of extra tools that you can use. Once you know my grid is going to have this number of points in it, they're all in a line in this direction, there's a whole range of tools you can use that can be used to make things very, very fast indeed. And even if you don't use those, you're typically going to end up with something that's still fairly fast. And I'm going to talk about why that's the case. So here's the sort of structured grid models that I use for some of my simplified problems to give you an idea of what can be achieved. So this is very, very standard. This is a very, very standard sort of simplified basin scale ocean model that you might use to study simplified problems in ocean turbulence. So this is a very, very classic problem. So broadly speaking, this is what's called the quasi-geostrophic equations. It's broadly speaking trying to model large-scale ocean dynamics. So you can think of this here. This is the near-surface ocean in this case. This is mid-depth ocean, say, and then the deep ocean. What you're looking at, perhaps the more familiar one, is at the bottom. That's the stream function for this flow here. And this thing that's peeling away from the boundary, that's sort of a model Gulf Stream-like phenomenon that emerges. And this top panel up here is a vorticity. It's the potential vorticity for this problem. But this is a very, very classic problem where we can use this to model what does turbulence look like in simplified ocean gyres with, say, a separating jet with multiple layers so we can capture different parts of the flow in the ocean. How hard is it to code something up like this to study this problem? So the numerics in this particular problem are incredibly standard. So the particular discretization is at least 50 years old. The time discretization is very, very standard textbook time discretization. There's inherent equations. You can use very well-known, very fast methods to solve this problem. These are not too tricky to code. It's fairly compact when you code these. The particular problem I showed you here, this one here had around 750,000 degrees of freedom per field. So you're looking at order 1,000,000 degrees of freedom per field, order 500,000 time steps, and you can run that in about 7 hours on a desktop. So that's a modest scale problem. There are parallel versions of these if you want to run particularly large problems, but here we've still got order 1,000,000 degrees of freedom, order 1,000,000-ish time steps, and this is comfortably possible to run on a desktop using a structured finite difference method. And you can step up the scale of the problem, so turn the resolution up a bit, turn the viscosity down a bit, exactly the same setup otherwise. So here's our near surface stream function, our mid-depth and our deep, and here we see our jet, and we've got much more small scale structures starting to emerge as we turn the resolution up and the viscosity down. That's the same code, I just turned the resolution up. So we're pushing something that's a bit bigger. We're up to 12,000,000 degrees of freedom, 3,000,000-ish time steps in this problem per field. So there's between 2 and 4 fields depending on how you count it. But we've gone up, say, an order of magnitude in the number of degrees of freedom. Okay, you might not want to run that in serial on a desktop. I actually did. It takes about 2 months. If you're patient, you can still do it. So it's still not that hard to do. And there is a parallelized, more complex version if you didn't have the patience to do that. And if you had the diagnostics, it slows down a bit. But the point is, this is very tractable. This is something that, I coded this up myself based upon a code by Pavel Berloff, but otherwise I coded it up myself. Didn't take too long. You can run it on a desktop and study the problem, and it's pretty fast. So what's the problems with structured finite difference and finite volume methods? So you get all these nice benefits. So you start to hit a couple of problems, particularly when you start to look at problems with complex domains or with multiple scale structures in them. So if you have a uniform structured grid, let's say a complex ocean coastline, then you can have problems associated with that coastline. You've got to truncate it in some fairly arbitrary way to do that. There's things you can do, but you start to make the coding more complex. And also, if there's somewhere in the ocean or in your problem where you think, I need tons of grid points there, that's where all the important dynamics are, it's tricky, it's doable, but it's tricky to do that in a structured code. So because you've imposed this rigid structure, you've lost the freedom to move your grid points around to conform to your dynamics or to conform to the domain of your problem. So unstructured finite element methods are different. They work around this. They use quite a different formulation. I'm going to give an example of the formulation actually later. But the practical result of the way that they're put together is that you end up with a lot of freedom in where you're going to put your numerical grid points in your model. So where in a finite difference code, if you were structured in uniform resolution, you may be forced to put one grid point here, one grid point to the right, one grid point to the right. Perhaps you hit an edge and you just say mask them out and say don't compute them, and then you end up with this it's called staircase representation of the boundary, and you can have problems associated with that, and you can at least see even by eye it's not a very accurate way to treat the problem. And you can imagine how this gets worse with complex boundaries. A finite element model basically lets, with some restrictions, but it lets you put your grid points in down with much more freedom. So here we can just say, well, here's my boundary, let's align triangles to land along the boundary. That's fine. And in fact here I've also said I want a bit more resolution up here, and a middle amount of resolution down here, and then a bit less down here. And that's fine, that's supportable, because you can just move your grid points around and add triangles and take triangles away until you get something that's compatible with what you've asked it for. And you have a huge amount of freedom in how you do this. You can use triangles, you can mix this up with other element types in general, you can allow highly anisotropic elements in general. I mean, here they're quasi-isotropic, but you have a lot of freedom when you write your code this way. So here's the sort of thing that I use these models to study. So this is the Fluidity code, which I'm going to mention later. Actually, this is interfacing with the tools that the bulk of this talk is talking about, but most of the hard work here has been done by Fluidity. So this is a classic lock exchange problem. Here we have the light fluid in red, and then the dense fluid in blue, and we have a lock in the middle, and we open it up, and we get a nice gravity current with Kelvin-Helmholtz, and then smaller scale processes and some numerical mixing in this problem. And what we're doing here on the right is where it's decided to put the grid points or the triangles. So initially we have lots and lots of structure in the middle, so we put lots and lots of resolution in the middle. And then the gravity current moves and flows, and the structure moves, and the grid points move. and the structure moves and the grid points move. So you have a huge amount of freedom in where you're going to put your model resolution, but with freedom comes additional problems and additional costs. So the particular problem being studied here was how does changing the mesh affect the solution? How do we have to be careful with how we transfer our data when we're changing our mesh? But you hit all sorts of other particular potential difficulties here. So you get a lot of freedom. It's particularly good if you have complex domains and complex internal structures. So in that latter case, I was taking advantage of the fact that we knew we were going to have a density interface, so we can track that in some way. But we have all sorts of potential drawbacks. The code, the bottom line is the code gets much more complex when you code something like this. The data that you've got on these triangles on an unstructured grid does not map onto a 2x2 array in memory. It's not just a rank 2 array in RAM. It's much more complicated than that. You need data structures to represent the triangular grid itself, data structures to represent the data on that grid, data structures to tell you how to compute numerical integrals on that grid. It gets much, much more complex. And all those nice numerical tricks you could use when your data was nicely aligned in a straight line and predictable, a lot of those tricks just don't work because the data is not aligned in a nice, predictable way. And worse than that, especially if you're using dynamic mesh adaptivity, you can have meshes turn up which are quite pathological, so your numerics needs to be quite robust in those cases. So you need to come up with some tolerant, very general and tolerant algorithms. General and tolerant often translating to more expensive in that case. So once you've gone through this, you've ended up with something that is both more difficult to code and something that's going to be slower in general. So typical slowdowns from moving from a structured to an equivalent unstructured finite element model. So slowdown factors of around 2 to 10 are reported. It can be much worse depending on the model and the problem you're looking at. So slowdowns of beyond 100 times I've observed. So it's much more expensive. With this freedom comes complexity and potential extra cost that you have to be careful of. So for the remainder of this talk, I'm going to go into a little bit of the details, particularly when you actually sit down and code these models, as to what's really good and why it's relatively straightforward to code a structured finite difference code. I'm going to hint at why it's much, much harder to write a finite element code, and then for the remainder of the talk, I'm going to talk about the tools that have emerged that let you cross this gap and code up these finite element codes in a much more accessible way. So let's go back. And let's talk about coding up a finite difference solver. So I'm going to start with a nice simple equation. I'm going to start with a simple ODE here, a second order ODE. This is a second derivative with respect to x here, some right-hand side data, and some nice boundary conditions. So this is a nice simple discretization. We can use a standard centered discretization on this. Standard textbook centered discretization. Everything is nice and straightforward. But what does it look like if you actually code something to solve this? That's the question. What does the real code look like for this problem? Okay, well, in fact, you probably need to use some linear solver on this problem, so I'm going to simplify it even further. Let's just look at this operator here on the left-hand side. Here's our representation of the second derivative, and ask, what does it look like if you wanted to compute that? Just to compute the action of that operator, the action of the discrete operator. So what does it look like to evaluate the discrete Laplacian in this problem? So here's some good old Fortran 77 to actually do it. So I've gone back deliberately to Fortran 77 because those languages are perfectly good for coding up these sorts of problems. Why is that? Because, so here's what the code looks like. So we have some language-specific details. So here's defining our data, defining what we're going to work on. But that's what's doing the heavy lifting. So we've got a loop in this case, but here, this is that line. So in order to evaluate this Laplacian, here's what it looks like in mathematics, here's what it looks like in Fortran 77, and it's one-to-one. It's really, really clear what's going on. You have the mathematics, you just translate that into Fortran code. Formula translation, that's explicitly what it's designed to be able to do in this problem here. It's really, really clear what's going on. And that's not language specific, we can go to any language we like. I mean, here's a bit of C++ that basically does the same thing. Okay, so the wrapping code looks a bit different, perhaps a bit more complex, but when you dig into it, there's the line. So if you want to compute the action of the discrete Laplacian, here's the mathematics, And it's just a ported version of that same code. It's again, one-to-one possible to see exactly where all these terms and all these factors are. It's really easy to identify the mathematics. And let's just step up the complexity very slightly, because we're going to look at some 2D problems in a minute. So that was just a 1D ODE. Well, let's go to the 2D PDE version of it, and we'll go to the two-dimensional operator, the 2D Laplacian. So we've added a d by dyy here. Again, nice simple boundary conditions, but when we go from our PDE up here, our Laplace equation up here, and we discretize it, we end up with the standard, here's just the standard 5-point Laplacian for this problem. Okay, so what does it look like if we code this up for real? And again, if you actually wanted to solve this equation, you'd probably have to wrap it in some linear solver, so let's just simplify it again. Here's our continuous Laplacian, here's our discrete Laplacian. What does it look like if we just want to evaluate the action of that, evaluate the Laplacian itself? What does it look like if we just evaluate this in code? Okay, well, Fortran 77 is still fine. We just add one extra outer loop, a few extra indices, up the rank of a few things, but the maths is just still there. It's pretty clear what's going on. So, again, we can identify each term one-to-one, each factor one-to-one. It's pretty clear what's going on. We have the mathematics, we have the code, and we can really see where the mathematics is in the code. Switch languages again, here's a bit of MATLAB. Okay, this one looks a bit worse because I've optimized it a little bit, so we're using vectorization in this case, but it's still there. It's more or less a one-liner, in fact, in MATLAB. So the point is, once you've got a structured grid like this, where we're differencing to the right, differencing to the left, up and down in this problem here, it's structured, that maps nicely onto our array in memory. We can just index into arrays and we end up with a one-to-one correspondence between our mathematics up here and our code down here. It's really easy to see what's going on in this case. So particularly finite differencing using structured grids, it's pretty easy to represent the data. It's just in an array. These are often built into the languages, so they're not necessarily, but they're often built into the languages that we use, which we use because they have that feature that we need to use here. It's relatively easy to relate the equations we've written down, our discretization, to the code that we're actually using to compute it on the computer. And as a kicker, it's likely to be quite efficient at the end. So particularly that MATLAB implementation was likely to be quite efficient because we vectorized it, but two nested loops are also likely to be quite efficient, and even if you've coded it in an efficient way, it's relatively easy for the compiler to work out what's going on and to speed it up for you. Okay, let's go to the finite element method. So we've got our 2D Laplace equation. Let's discretize this using the finite element method. I'm not sure how familiar people are with discretizing the finite element method, so I'll just run through the steps in this problem. So here's our equation. I've just written it down as the del squared. And here's the usual methods you go through to derive a finite element discretization. So I'll just go through it very briefly for those who are not familiar with it. So we start with our PDE. Well, we can multiply that by anything we like, and that's still going to be a true equation. And we can integrate that, and that's still going to be true. And then we can integrate this by parts, and that's still going to be true. And in fact, as long as we knew that the solution that we had in here satisfied the boundary condition and all the derivatives made sense, we could actually unwind these all the way back. That's how you derive a finite element discretization. So what we've said is that our original equation implied this integral must be true. We just multiply, integrate by parts, and in fact you can unwind it and go back to where you started. So these are equivalent subject to smoothness and boundary condition requirements. And what you do in the finite element method is you say, well, let's find so what do we multiply it by? We multiplied it by something. Well, we needed to think of all possible functions that were sufficiently smooth for this to all work, but let's restrict ourselves to saying we've multiplied by something piecewise linear, say. And then we say, what's our solution? Well, our solution is also going to be piecewise linear. And then we try and find the piecewise linear function where this is true for all piecewise linear zeta. That's basically how the finite element method works. So what it boils down to is you turn the PDE into the weak form PDE down here, and then you multiply through by lots of different things you care about, and try and find, say, a piecewise linear function where this makes sense and yields a solution. That's how it works. So it boils down to being able to compute these integrals. If you actually want to solve them, you have to compute these integrals. So what we're saying is let's find something which is, say, piecewise linear or piecewise quadratic or some other function, as long as it's got the right properties, such that all these integrals look the same when we drop in a particular type of function for zeta here. That's how it works. So it boils down to being able to compute the integrals. That's how you actually solve the discretization. So what does that look like in code? Okay, well, this is the finite element representation of a discrete Laplacian, or at least that's the bilinear form you get from the discrete Laplacian. So let's, again, as we did for the finite difference method, let's just take this left-hand side and say, what does it look like if we want to evaluate the left-hand side in this problem? There's our left-hand side. What does code to evaluate that look like? There's not enough space. There's really not enough space. What's going on? Well, we need to compute integrals of, say, some piecewise linear function defined over triangles times by some piecewise linear function defined over triangles. We've got to take their derivatives and integrate it over all the triangles. There's a lot of work going on to do that. That's really quite a lot of work. This is the closest I can get to something that fits on a slide, but even here I've cheated. So this is the sort of thing that you end up coding if you want to evaluate the sort of things that turn up in an unstructured model. This is the sort of code you end up writing. I've cheated, so the detail's not so important, but you can see I've cheated because I used an external tool right at the start. This external tool is tens of thousands of lines of Fortran code. So this is nice and compact, but it's only because I've used an external tool. Actually, I'm using Fluidity's internal structures. And there's all sorts of extra things going on. So we've got unstructured data, we've got the data defined on the unstructured grid, then we've got all sorts of extra integration stuff we need to worry about. The integration, where's that integral? Well, here's a sum over the triangles, and then down here somewhere, you can just about see we've got some things that might look like the mathematics. The mathematics is really obscured. And actually, this is also really inefficient as I've written it. This is really not a good way to write this, at least for many types of problems. So when we actually code up an unstructured finite element model, what sort of problems do we get? So the data types have got much more complex. If I just go back, we had to use an external library, and then we had to use some representation of our triangles, some representation of piecewise linear functions, say, over our triangles. And we also, buried in that, we have to represent the grid, we have to represent our discrete solutions, we have to know how to do integration over our grid, and the discrete equations are there, but only if you really know where to look for them. There's no way of just highlighting, here's the line. It's really obscured because we had to wrap it in all this extra code in order to be able to do it. And as I hinted at, this would also be quite inefficient as I've written it. It's much more difficult to obtain an efficient implementation in this case because it's going in and out of this library. It's going in and out of these calls. It's much, much harder for the compiler to tell how to optimize it. It's much, much easier to make mistakes that will make it inefficient in this case. So what I'm going to talk about for the remainder of the talk then is how do we fix this problem. So if I come with the premise that I want to be able to write a finite element code, but I want to be able to do it in a reasonable amount of time with a reasonable level of efficiency and in a way where I can see, here's my discrete equation, here's my code, so I can relate what I've written down in maths to what I'm writing down in software. So there are tools to do that. I'm going to talk specifically about the tool that I use and then the extension that I worked on a few years ago. And the way to think about this is to go back to the start and ask, what were the original programming languages we're using designed to do? This is one way of thinking about how you do this. So we can go back, this is going back right to the days when people were designing Fortran. This is the preliminary report, the formula translating system. So I'll just read this briefly. The IBM Mathematical Formula Translating System, or Fortran, will comprise a large set of programs to enable the IBM 704, I think that's one of these room-sized machines, so this is going back a while, to accept a concise formulation of a problem in terms of a mathematical notation and to produce automatically a high-speed program for the solution of the problem. So what it was designed to do was for you to be able to write down, here's my mathematics, write that down, and then that to be turned into a high-speed program. That's what it's for. And as I showed earlier, Fortran 77 is perfectly fine if you want to do that for finite difference code. It's perfectly possible to write down your finite differencing, and you can see here's the mathematical representation, and that gets compiled into a working binary for you by the compiler. This doesn't work so well with unstructured finite element codes. This paradigm gets broken if you're coding it by hand. So here's the general principle that I think summarizes how code generators work, the sort of tools that I use work, which is that the syntax that you're using to express your model code should match as close as possible the maths that you've written down. So I have my ocean dynamical equations I want to solve. I write down my equations. I want to be able to write those down and the computer to deal with it. I don't want to have to code all these extra library calls. I just want the computer to deal with it and turn that into a code that's going to work. So code generation, the way that the code generators work is that they introduce a syntax to write the type of model you want to write and then do a source-to-source translation and write your low-level code for you. That's how they work. So the specific tool that I tend to use, so there are a few different types of tools around, but the one that I've been using for a few years, it's called the FEniCS system. So here's how it broadly breaks up. You introduce a new language, it's called the Unified Form language, that lets you write down a finite element code, and then there's tools that turn that into working code for you. Actually C++ code in the end that you get out. I want to write down my mathematics, it deals with it and generates the C++ code, and specifically for finite element models in this case. So let's go back. So we had an unstructured finite element model, and here was the discrete representation we came up from the left-hand side of our Laplace equation. We needed to be able to evaluate integrals that look like this in order to be able to solve, say, the Laplace equation on an unstructured grid. What does code to evaluate this look like using a code generator? Now it fits. There's the code. That's what it looks like if you're using FEniCS. So in fact, the line that matters is that one. It's there. And that's like the mathematics. That's the difference here. So if we break apart what's going on, so there's, again, exactly like when we wrote a finite difference code using Fortran. When we write a finite element code using the FEniCS system, we've got some wrapping stuff at the start, which I can go through, but then at the end, that's what we care about. We have an integral of grad, please compute it. That's what those two lines at the end mean. What's the wrapping code? Well, it's not too involved, so we said let's actually use the library, let's use the tools, then let's define, well, it's an unstructured grid, it's actually an unstructured representation of a structured grid here, but it could be any grid you wanted. Then we want, here this is saying I want piecewise linear solutions over the triangles, and then we're setting up our representations of the things we want to compute with, but the bottom line is here is what's doing the heavy lifting. And that now looks like the mathematics. That's not a screen of Fortran, it's basically one line, one or two lines. If you actually run the code, here's what happens. So here's just that same code again. Here's what happens if you just run Python on this and say just run this calculation. It doesn't actually do anything, but it does compute it in this problem. What happens is that, so it starts passing the Python, and then it hits something here, and it says you wanted to talk about piecewise linear functions on triangles, and it needs some code to be able to work with those, so it goes away and compiles it for you. Goes with it. Down here I was computing some data. I wanted to be able to just evaluate some data so I can actually do a calculation. So here's a little piece of code. Okay, so it goes away and it compiles that into C++ so that I can interpolate this function. But then when it gets to the important bit of code down here, it says, please compute the integral that I asked for. So here's the integral I want to compute. Please actually compute it. And then it goes away and writes code to actually do the integral for you. That's how it works. And if you run it again, it's got the code already. So it doesn't go away and recompile it. It just pulls it out of the cache. You don't ever have to look at it, but if you want to work out what did it actually do here, you can go and get it. If you go and look at what code did it actually write, well, here's the files it actually wrote to be able to actually do that integral. It's not really supposed to be human readable, it exists. I think the most important file actually is this header file here, and then it's got some compiler wrapper stuff around it. These things here, I think this is around 1,000 lines of C++ code. But it's done a lot of work for you there. You just said, I wanted to compute it, and it went away and dealt with it for you, and wrote the code to compute that for you, based upon the high-level representation. And we can go one step further in this case. So I shied away, even the finite difference case, I shied away from actually solving the equation. I just said, here's how you evaluate a Laplacian. Well, okay, let's actually just solve the equation. What does that look like? It's a few extra lines, actually, in this case. So it's very, very expressive and very, very powerful. All we've really had to do to solve the entire problem is say, construct the matrix representation of the left-hand side, compute the right-hand side here, here's the right-hand side, and we've had to add some boundary conditions to the problem. But again, the important lines are this one here, here's the left-hand side integral, and this one here, here's the right-hand side integral. And this really looks like the mathematics. It's very, very compact and very, very expressive in this case. So what the code generators do is they give you a syntax, at least this type of code generator, it gives you a syntax which lets you write down a finite element model in a way that's very, very close to the mathematical notation, and then it uses source-to-source translation tools under the hood to actually deal with that and turn that into a running model for you. What that allows you to do, so I'm going to talk about what this means in a moment, is once you've got a high-level representation, a lot of how are we going to make this run fast for this particular architecture, how are we going to run it in parallel with MPI, how are we going to thread it with an OpenMP, well, that's all details dealt with by the code generator. If it wants to optimize the code, it can go ahead and work on optimizing your code. And that's something, in particular, when I'm writing an ocean model, that's something I don't want to have to think about too much. If there's ways of making my code run fast, I'd much rather the tool did it for me in that case. It has some really powerful extra benefits as well. Once you've got a high-level representation of your code, you can start to manipulate your equations after you've written them down. So the computer can start to work out, well, you've solved these equations, let's do some extra calculations that use the solution you've got at the end. So if you've ever used algorithmic differentiation tools, say running a joint code, if that's a problem you've ever studied, you can do this actually at a very, very high level and just say, please derive an adjoint code. And it's got all the equations, so it can go ahead and do it for you. So that's something, there's a tool called Dolphin Adjoint that will actually add that functionality. But you can really start to work on the optimization of your code. So this is talking about how you raise the level of the abstraction. How do we raise it a little bit further? So this is actually something that I've done. This is something I worked on with Patrick Farrell. The way you can raise it even further is suppose I'm solving a time-dependent problem in this case. So here we have a time-dependent problem. This is the heat equation. And you can go ahead and discretize it. I won't go through the details this time, but again, this is a fairly standard discretization. You can more or less see here's the time derivative term, and then here's a term representing the diffusion on the right-hand side. So how do we go ahead and write a solver to solve this code? Well, if you just use the tools that are available and go ahead and write the code, here's the sort of thing you might end up with. And again, here's the important lines at the bottom, where it's saying, please solve, this is an integral of this test zeta times by our time difference. And then I brought this on the other side, plus integral of the grad of the test, kappa times by, it's all here. Here's the actual equation, just in code. Please solve it, and please time step the equation. Actually, if you do that, that's actually really not going to be very fast for this model. So the reason this doesn't really work, let's dig into the time loop. Here's where the important work is going on. Again, it's very, very high level, very, very expressive. We've just written down the equations, and in this case, I've just asked the FEniCS system, please solve it, and it's dealing with working out the matrices and calling them the solvers for you in this problem here. Where this goes wrong is when we start to time step, there's lots and lots of things that start to be constant in time. So in this problem here, we knew that the diffusivity is not going to change in time when we're solving the heat equation. We know our mesh isn't going to change in time. We know many of the matrices that turn up in this are not going to change in time. So we have lots and lots of things that we could be computing once and then just caching for all time. And this gets drastically worse when you start to have multiple equations. So and I have models that have several dozen equations in them. The sort of, if you wanted to code them up in an optimized way, you'd have to by hand work out which bits you could compute and cache. So let's not do that. Let's go back to the general principle and just add a syntax that lets us write down time discretizations. So this is something that I added. There's an extra extension you can wrap on top of these code generation tools. It's just called unimaginatively the time stepping library at the moment. And what that does, it says, well, okay, here's the equations you want to solve in time. I will go ahead and work out which stuff is going to be constant and can be cached and will not be recomputed. So what does that look like? Again, it's very, very similar. So here we're using the FEniCS system, and then we're using the extensions from this library, and the only differences that really turn up are that we have a way of writing down, so we have integral of a test, well, temperature at the future time minus temperature at the present time. And then temperature at the past time plus temperature at the future time. It turns up in here. We just added a way of writing down subscript n plus 1, subscript n, and then the tool takes this code here and works out, well, actually tons of stuff in here can be computed once and reused for multiple time steps. So again, we just have a very, very high-level expressive representation here of a time-dependent code, and it's optimizing at the equation level and caching stuff for you in this problem. So if you go ahead and run that problem, if you actually run this equation, what happens? So here you can see the code generator doing its thing, but then here's the time level optimization. So it says, well, we're solving for a future temperature, and then it notices that the matrix in that equation is actually constant, so it caches it and stores it, and it notices it's going to solve that with the linear solver that's also going to never change, so it creates a linear solver and never creates another one, and then it also notices that tons of stuff on the right-hand side doesn't change as well. And it optimizes that away. And that's all just done under the hood for you. So in this case, it's got two integration optimizations, and also there's a matrix optimization. So I know, how much time do I have left?
You've got another 8 minutes.
Okay, so I'll run through just a hint at the applications that I'm actually using this for. So that's how it all works under the hood. So I'm going to give a hint at how this works in applications and how fast you can expect these sort of codes to be. So first of all, let's just do some benchmarking. So we'll aim fairly high to get started. Let's solve Navier-Stokes. Okay, so this one here is using a fairly advanced finite element scheme. It's using actually a discontinuous Galerkin scheme for one of the fields. A moderately complicated time-stepping scheme. It's using a type of approximated Crank-Nicholson. But this is a Navier-Stokes flow solver that's basically intended and designed to look as much as possible like the Fluidity CFD internals. It's basically designed to try and look like that. So how long is it? It's 360-ish lines long, the whole code. And that includes all sorts of debugging. It's actually, the stuff that's really solving the fluid equations is about 260 lines long. As I said, Fluidity is hundreds of thousands of lines of Fortran, all in. Here we've got a few hundred lines. Although Fluidity does tons of other stuff as well, if we're being fair. Okay, so if we just solve, say, a classic driven cavity problem, so we just drive it on the top and it overturns. Here's its stream function. How fast is it? So if you turn it on with the optimizations that I talked about, where you write down your equations in a very high-level way, including a way of representing our time discretization, let it go ahead and optimize it itself, then we're somewhere over twice as fast as the Fluidity CFD code in this problem, approaching 3 times as fast. So this is a code that was basically written by myself in a few hundred lines of Python. Fluidity had a team, it's hundreds of thousands of lines of Fortran, and it's faster, quite a bit faster in this case. Although Fluidity has many extra features, to be fair, in this problem. Okay, so if we look at how much speed up are we getting from, say, doing high-level optimizations, it's somewhere just over 1, I think it's 1.7-ish for this case. So the fact that we're using tools to under the hood do optimization is giving us speed up as well, although it's not terrific in this problem. Change equations very, very slightly. This is closer to the ones I showed at the start on structured grid models. This is basically the same equation but just with one layer. So this is now got quite an approximated representation. Here's this model Gulfstream again. So we're just solving some very, very simple equations in a box with a wind-forced ocean. Very, very simple approximation here. And when we start to use the tools to do optimizations, the time discretization itself, we're getting much, much more significant speed up here. Somewhere around a 4 times speed up in this problem here. On all that we're doing here is we're writing down a very compact representation of the code and letting tools go away and turn that into working C++ code for us. Again, this is 160 lines of Python once you've cut out most of the debugging code. So it's very, very compact. And we can step it up again. So this is now a version of the quasi-geostrophic flow solver I showed right at the start. So there was a very, very simple finite difference code that you could write and run very, very quickly, where you can write a comparable finite element code. In this case, this one here has actually got some more complex numerics going on. Some very particular properties were needed for studies in ocean turbulence. But we've still got a code that's a few hundred lines of Python long. And if you dig into the code, you can still see here's that equation, here's the mathematics for that equation, here's that equation, here's the mathematics for that equation. So as I'm running out of time, I'll drop one more hint for the sort of things we're studying. This is something a bit more recently. So this is digging more into the details of the sort of things I use these tools for. So I study problems in ocean turbulence. And one of the things you might want to do is you might say, well, I have small-scale turbulent fluxes in this flow. Can I try and work out a diffusivity associated with those turbulent fluxes? So one way to do that is to take turbulent fluxes and a turbulent diffusivity and just try and solve an optimization problem. And I won't go into the details of where these come from, but there's some physics buried into why it has this very specific form. So we say, here's our small-scale turbulent fluxes, here's our proposed representation for those fluxes. We're going to add some prior expectation of smoothness on the diffusivity. We want to solve this optimization problem, and then this is just basically screen grabbed out the code it was to solve the optimization problem. So this one here is, psi is going to be our representation of this term here. This is our data representing this term here. They have an inverse Laplacian, so we solve that by a Lagrange multiplier, and we have this term, which we just write down. So this looks exactly like this term. We add them all up, and we differentiate them, and then we can ask it to solve for where the derivative is 0, and solve our optimization problem for us. And this particular problem here, this one was about 180-ish lines of code to solve an optimization problem for kappa in this case. So I think I will conclude. Oops. Here. So there are a couple more examples. So I'm working on combining this with dynamic mesh adaptivity. So you can use the high-level code to study how dynamic mesh adaptivity can be improved in particular calculations. But I think I'll move to the summary as I'm short on time. So the code generation tools that I'm using, their key features are they allow very, very rapid development of finite element models. It is possible to sit down and write models really quickly. For simple equations, they can be done more or less in minutes, but even if they're complex equations, you're not looking at a huge time investment. It's particularly useful if you want to do rapid prototyping. So if you say, I have this numerical method, let's see how that works, well, you just code it and see how it works. I have this proposed turbulence closure that I want to drop into this model, where you can just code that in, and it's only a few small changes relative to what you had. And the reason is you have a very high-level expression, and you have high-level ways of manipulating those expressions once you've got them. I'm specifically applying them to problems in ocean turbulence, and I'm happy to talk to you about further details about the specifics of what these are being applied to. But to conclude, I will mention there are a couple of challenges associated with this. So these tools are still being used to write finite element models, and I mentioned right at the start that they tend to be slower than finite difference codes. So the challenges associated with decreased costs on unstructured grids, they're still there, so you still have to be careful. And you also have to be careful because there are problems that you can write down that you're interested in that cannot be written down in a high-level representation. So if you come up with some scheme that says, well, I want to have this particular complicated term here that the people writing the tools never thought of, then you can't write it down, and the code generators can't generate the code for you. And also the high-level manipulation won't work either. So there is a potential note of caution there, so you do have to be careful when you come to things that are very customized and very specific for particular applications. Thank you. I think I'll stop there.
This production is brought to you by the University of Edinburgh.